Welcome back, everybody. So in class, we talked a little bit about power, and I wanted to take a moment to show you a little bit about kind of where the power equation comes from. And I'm going to start a little bit by talking about energy, which is something we're very familiar with. And perhaps unsurprisingly, there's a transfer of energy in a circuit. As we know, the battery is a chemical potential energy store that turns that chemical potential energy into electrical energy. And then that electrical energy is going to become usually something like kinetic energy that heats up a resistor or a wire or a light bulb. The way that we usually like to measure that energy is not by measuring the energy, but by measuring the power. If you remember back to mechanics, we talked about power as the time rate of change of energy, dE dt. And we can basically just take this Q times V, which we know is the change in electric potential energy that a charge undergoes, plug that in to this energy here, take the derivative. As long as our voltage, our potential difference remains constant in time, we can take that V outside of the derivative, and we just have an equation which looks like V times dQ dt. And as we talked about last week, dQ dt is the current. That's the definition of current, right? So this is how you get that the power is equal to I times V. A few questions that I will leave you with is, does this equation make sense? What are the ways in which you would make sense of this, given what we've done in the class? Why do you think this equation is useful? And how do you think we can use it to determine the total energy delivered to a resistor?